Good afternoon. Welcome to the course Thermodynamics of Materials. Today we are into lectures 99 and 100. So we are discussing the four issues that make thermodynamics a difficult subject for the students. And the last issue was concept of equilibrium. And just we started only. Just we made some introductory comments. Like I said, that some students think that equilibrium state is the state at which the forward reaction rate equals the backward reaction rate, but they don't know that this is a kinetic statement, not a thermodynamic statement. And for thermodynamics, some students although know that it should be either free energy minimized under constant pressure temperature, free energy of the system is minimum, or alternatively delta G is 0 at equilibrium state. But question is more deeper. What will happen? What happens when what happens when we actually need to solve the simultaneous or multiple reactions, multiple equilibrium state of multiple, not single reaction, equilibrium state of multiple reactions instead of a single reaction system where we have simultaneous equilibrium. So simultaneous reaction, simultaneous equilibrium, so multiple reaction. So we actually will look into this issue and we will see that the concept of equilibrium may be a little bit involved. That's why we have taken up this as a issue that makes thermodynamics a difficult subject. So let us discuss this point, as I said last day, with three examples presented in the form of a question answer discussion below, to be taken up in the next class. So today is the time that we will take up. Okay. So I want to remove all these things. I want to make some space. So I remove this today. I don't think you have any difficulty if I start from the example with for first example. So just so sorry. So these are the, so we'll take up the first problem. So the first problem is, let's take the question first. Example A. Suppose in the form of question and answer. The question is, suppose we have initially taken zinc sulfide solid and sulfur S2 gas at 1 atmosphere pressure and temperature T okay, in a closed in a closed in a constant volume closed system, in a constant volume closed system. and we allowed it to equilibrate, and we allowed the system to equilibrate. We allowed the system to equilibrate. Given that that the partial pressure of sulfur dioxide, that the partial pressure of H2 gas, which is PS2, which is PS2 gas, which is PS2, is 0.5 atmosphere, 0.5 atmosphere at equilibrium. Short, in short, at equilibrium. At equilibrium, what will be the partial pressure? What will be the partial pressure of zinc vapor? Pressure of zinc vapor at equilibrium. This is the question. The first question. Second question, will there be any liquid zinc formation? Any liquid zinc formation? The second question. Third question is, will there be any other, will there be any other sulfur related species, sulfur related species in the system is like 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 S4 gas, S6 gas in the system at equilibrium. So three questions are there. What will be the partial pressure of zinc vapor at equilibrium? Next, will there be any liquid zinc formation? And last question, will there be any other sulfur related species like S4 gas or S6 gas in the system at equilibrium? So answer. Let us consider the equilibrium. Consider the equilibrium. Zinc sulfide solid goes to zinc vapor plus half H2 gas. Delta G0, just I call it A plus BT, is where A is given and B is also given. So as we obtain in data books, given. First of all, how will proceed? Find KT, equilibrium constant at temperature T, using what? Using The number of times we do this using delta G0 is minus RT ln minus RT ln minus RT ln is okay. RT ln, as you know, this we often use. We, in fact, every time we use this, where Kt is what? The equilibrium constant. Kt is what? Partial pressure of zinc, partial pressure of S2 powered half, and activity of zinc sulfide. This is solid, actually solid. So this is what? This is pure. So the activity is 1. So we know this. So P zinc is PS2 is how much it is given? PS2 is given as how much? Equilibrium value is given 0.5. So 0.5 power half, and Kt is also known. Kt is known from this. This Kt is known. So everything is known. So we can find out. This leads to Pzn is known. You can given here equilibrium. Equilibrium constant refers to the activity ratios at equilibrium. So this is Pzn equilibrium. Okay, that is the question. So Pzn equilibrium is found. Okay, Pzn equilibrium. Okay, is what is this? Partial zinc at equilibrium. So you can write Pzn equilibrium. It is understood, but you may write also Pzn equilibrium is first question is answered. What is the second question? Will there be any liquid zinc formation? So for this, we have to find the saturated vapor pressure of zinc first. Saturated vapor pressure of zinc, and if this pressure of zinc exceeds that saturated vapor pressure, then only liquid zinc will form and continue forming. Okay, so let this I discuss. So next question is next question is whether liquid zinc will be formed. To answer this, we have to answer this. To answer this, we have to find Pzn0, which is known as at the temperature T saturated, which is also saturated also, that is equilibrium. Implied vapor pressure of zinc liquid zinc liquid at temperature T. This is it. We have to find this, and how we can find this? And if Pzn exceeds Pzn0, liquid zinc will form and continue precipitating until so since it is greater than this, it exceeds this, so zinc vapor will condense into liquid. As a result, vapor pressure will fall, and continue decreasing, and finally when it will be equal to pz at 0, then the process will stop. So you may write this until continue precipitating until pzn, it decreases continuously because zinc from the vapor phase constant volume reactor, constant volume closed system. So zinc vapor is condensing. So as a result, the partial pressure of zinc from the vapor phase, zinc is transferring to the liquid phase. So vapor pressure of zinc will start decreasing. So now it is greater. So if starts decreasing, a point will come when this will be equal. These two will be equal, and then there is no question of any more zinc liquid formation. So we may write this that P0 until Pzn drops to Pzn 0. Pzn 0. Now question is, what is the, how will you get the value of Pzn 0? How will you get the value of Pzn 0? We compare this Pzn with Pzn 0. But how will be, so but how actually the value of Pzn can be obtained? Achha, how will you get this? The value of Pzn 0 saturated vapor pressure at the temperature T can be obtained using the equilibrium, can be obtained using the equilibrium which equilibrium? Zinc liquid goes to zinc vapor, for which again delta G0 in the form of A plus BT obtained from data book or textbook given in for which digest, so from which you get again and find KT in the same manner as delta G0 is minus RT ln K. So KT is what? Find KT, and KT is what? Write this Pzn by activity of zinc liquid. Now you can write at equilibrium always equilibrium you can tag at least once, or who are beginners, you can always write this equilibrium tag. Otherwise it is implied because it is linked to the equilibrium constant. So this will be all related to equilibrium, pertain to equilibrium state. So anyway, still you may write this is what is, this is 1. This is pure liquid standard state. 1 is Pzn, and this is your Pzn 0 T. So getting this value, you compare this value and you comment and decide whether it will liquid zinc will form. So this second question is answered. Now third question is, will next question is whether, I am writing, next question is whether the species like, whether the species like S4 gas, S6 gas will be present in the system, will be present in the system at equilibrium. Question, this is a question. So answer, again answer, will continue to answer this. So to answer this, consider the equilibrium To answer this, consider the equilibrium What equilibrium? 2s2 gas goes to S4 gas. Again, delta G0 for which is given A plus Bt form, given for which now you get K, and now find Kt. Find Kt in the same way. So delta G0 is minus RTL and Kt, and Kt is what? Tell me here, see the equilibrium, PS4 over PS2 squared equilibrium. Now this value is given at equilibrium as 0.5 squared. So Kt is known. So you can get out PS4 at equilibrium. You can find out. Okay. You can find out. This means you can find out. Okay. Solving this equation. So similarly, let us complete this. I'll give a star mark. I am removing this question. First question. So let me write. A is this. I am removing this answer, this part. This is over. So I am making some space here. This is a question A. Okay. A actually the last part. So similarly, write this. Star there. Star. Just one line. Similarly, consider the equilibrium. What equilibrium? S6 and S2. 3S2 gas goes to S6 gas, and again delta G0 is A plus Bt, given and find K, equilibrium constant K is PS6 by PS2 cubed equilibrium. This is giving 0.5 cubed. Okay. So and this is known from delta G0, and this leads to PS6 at equilibrium being known. So all three questions are answered, and we have considered multiple reactions and simultaneous equilibrium also. So this happens. Okay. Now you see these are actual clue whether liquid zinc will be formed. When this question is asked, this is kind of clue, kind of hints, kind of help. You are directed. Reading question, you are led to the answer, but you have to think for yourself. You have to think yourself that whether liquid zinc will form. What species will be formed at equilibrium if it is given? Not mentioned liquid zinc, S4, S6. You have to find out. You have to explore this. You have to ask yourself what other species may be present, because there are known species. Other known species like S4 gas, S6 gas, will they not be present? This is the question. Okay. This is similarly the zinc vapor, liquid zinc will it not form? At least check liquid zinc, because liquid zinc vapor pressure is not much, so it is easy to exceed that. And if it exceeds, then the liquid zinc will form. So this type of things. Okay. So but anyway, given the Hence, you see it is a multiple reaction system, and we are dealing with simultaneous equilibrium. So this problem A is over. So we will now take up B next. Next question dealing with concept of equilibrium. B. That's right. So quickly remove this. This is all over. First, second, and third. Then this topic of 4 issues will be over. So let us move on to the next. So next is what is the question in the form of question and answer. So first, let me give you the question. What is the question? Suppose we have initially taken a mixture of air solid, AO2 solid, and oxygen gas and O2 gas, in a constant volume, closed system, at 1000 Kelvin. Find whether A will be whether the A solid whether the A solid will be oxidized to AO2. Oxidized to AO2. This is our questions. Okay, AO2 solid, and 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 find the equilibrium partial pressure of oxygen at equilibrium. So this is actually two parts. Find whether A will be oxidized to AO2 and also find the partial pressure of oxygen at equilibrium. Okay. Next is in this next part, in this equilibrated state, some BO solid are added. Are added. If if some biosolid are added, will the biosolid be dissociated into B solid? This is the question. Okay. So answer, we are first to find the equilibrium constant, and the equilibrium of the reaction constant K of the reaction. Reaction is what? This reaction actually, it is A solid plus oxygen gas goes to AO2 solid. AO2 solid. Okay. AO2 solid at 1000 Kelvin. At suppose for the reaction A solid plus oxygen gas goes to AO2 solid, call it reaction 1, delta G0 is A plus Bt as before given. Is given. Delta G0 is A plus Bt is given. Now again, so what we'll do? We have to find the equilibrium constant. How? Find K using K 1000. Find K 1000. Actually, we write this way: AO2 equilibrium. This way we write actually. Find, because there is another system coming. So AO2 equilibrium constant is for find K from using the relation using delta G0 is minus RT ln K. Next find, so next find, one is K, another is Q. Q is actual. Next find, and we will compare Q versus K. You know Q less than K means delta G is negative. Next find Q, next find whether Q, the quotient in the actual state, activity quotient actual state, and this is the activity quotient in the equilibrium state. In the equilibrium state, actual state, K versus Q is less than, find if Q is less than K, and if when this happens, that is, or find whether delta G is delta G0 plus, let me do this, find whether delta G is delta G0 plus RT ln Q is negative. Same thing. If Q less than K means delta G is negative. Delta G is negative to ensure spontaneity of the reaction. Which reaction? Of the of the reaction 1 means this reaction. This is very easy. We have already solved many problems, so this is easy, but it will be complicated when B will come into this picture, and I will say something, okay, that I have already mentioned that, but today we will again take up that to ensure spontaneity of the reaction 1, of reaction 1, to spontaneity of reaction 1, okay, this is very good, to spontaneity of reaction 1. Suppose K turns out here from delta G0 K equivalence turns K1000. Temperature is very important. Equilibrium constant is a function of temperature. It turns out to be 100. K turns out to be 100. That is K is what? You write this expression for this reaction. K is what? That is right. K is K1000 for this reaction. K1000. K for these reactions actually, right? Reaction 1 actually. Or what I have written here. Okay, AaO2 I have written here. AaO2 means for this reaction. Equilibrium constant for this reaction turns out to be 100. That is K is what? Activity of AO2 over activity of A. Write this solid, and this is your PO2. K1000. Okay. Right here, K is this. This is what? Equilibrium. What is this? 1. Pure substance, activity 1. This is 1. This is 1. This is what? 1 by PO2 equilibrium. And obviously, what is value of K is what? K is what? We know the value is what? 100. We have considered 100, so 100 or PO2 equilibrium for which one? Which system? AO2 system, and what temperature? 1000 Kelvin. You give all these attributes, equilibrium etc. is how much? It is 0.01 atmosphere. So this is also answer. One answer. This answer, find the partial pressure of oxygen at equilibrium, and this is this value. And now this question is not answered yet. Find whether A will be oxidized to AO2. So we see this. So we see as K is 1 by PO2 equilibrium. So what will be the Q? Q is same, similar, only similar expression, only instead of equilibrium actual. What is actually present in the system? Now what is this value? So what is PO2 actual is what? You tell me here. Tell me. Q is what? What is the actual value in the system? We are taking oxygen gas. Am I using? What is actual? I mentioned or forgot to mention one thing in the question, that is at zero, an oxygen gas at 0.5 atmosphere. Oxygen gas, please, here. Oxygen gas at 0.5 atmosphere. This is actually present. So what is the system like? System like this actually. If I may draw this here, constant volume closed system. So what you have taken? A solid, AO2 solid. Actually, let me write first. Oxygen gas, what pressure? 0.5 atmosphere, and A solid and AO2 solid. This is the system. The system. Initial state of the system. State of the system. Okay, oxygen gas is at 0.5 atmosphere, closed system, constant volume. Okay, this, and now reaction takes place. And we have, let us see whether reaction will take place. Now it will be Q is actual, Q2 actual. Sorry, I missed this. Very sorry, but I have given here. I have filled it in. So what is this? 1 by 0.5. How much it is? 2. So 2 is, what is the K value of K? K is 100. Okay, 100, from which we get PO2 0.01. So 1 by 0.01 is 100 back. So 2 is less than 100. That is Q less than K. That is delta G is negative. Delta G is negative. Q is K. That is delta G is negative. Hence negative means reaction 1 will occur, spontaneously occur. Hence reaction 1 will spontaneously occur. That is, question is what? Find whether the A solid, that is A solid, will be, that is A solid will be oxidized to AO2 solid. So this is actually, we have actually this. Now I can give this initial state. So we find what? What we find? What is the equilibrium state? You draw here, you tell me. I am just writing short. A solid still, A, AO2 both are there, but only oxygen is O2 gas. What is the PO2? PO2 is reduced to what value? It is, equilibrium value is what? 0.01. 0.01 atmosphere. This is a certain temperature. T is 1000 Kelvin. This is also 1000 Kelvin. Okay, this is my thermostated. I have not drawn that 1000 Kelvin. Okay, so this is what you like, initial state. This is the equilibrium state of the system. Now you are doing something very interesting. You are now adding some in this equilibrated state. You actually some BO solid are added. In equilibrium state, some BO will be added. Follow this. BO solid. This is a barrier here. BO solid. This is equilibrium state. Now you add BO solid. Question is, will this BO solid be dissociated into B solid? So since multiple reactions is coming, and here there is, you have to consider one thing. Can I right? I just remove all this what I remove now, last part. It is last part actually. Two answers are there. So here, right, it is also answer. This is answer. This is answer. A solid will be oxidized to oxidized into AO2 solid. Okay, oxidized into AO2. So this part is over. So next take up from this star last part. Right here, last part. Last part is what? If we have added BO, so what is this? Last part, let us see. Now BO solid, let us BO solid describe the problem. Now BO solid is added to the equilibrated system glass obtained to determine what is the question? Will the BO be dissociated into B solid? To determine whether BO solid will be dissociated into B solid, is it into find the equilibrium constant. Again, equilibrium constant, symbol is K, for the reaction. What is the pertinent reaction? Right? Remove all this unnecessary. Only this is important. Okay, this is also in the figure, it is given here. So now BO solid is added. Here it is added. This is the equilibrated system. And BO now it's okay. It is at equilibrium and nothing will happen. But you are disturbing the equilibrium by addition of some foreign substance, like say BO, some other substance like BO, and BO will interact with this. So this is actually a multiple reaction, and multiple equilibrium you have to consider. But there is another hitch here that I will discuss. Q less than K in this business, you will come to this point soon. Find the equilibrium constant K for the reaction. What reaction? Write this. Your solid must dissociate. So obviously this will be the reaction 2B solid plus O2 gas. Again, as you know, delta G0 is A plus BT type given. Okay, A plus BT given. So suppose KT K1000. Okay, suppose K1000. Which system? This is actually, we write this BOB system, or we write, call this equation 2. Call this equation 2. This is BOB, or you can write equation 2. You can write equation 2 or K1000 BOB is what? Or this equilibrium constant for this reaction. This means equilibrium constant for this reaction, suppose turns out to be, using this delta G0 is minus or tail N K. I should not write. Okay, turns out to be 0.001 atmosphere. Okay, turns out to be I'm sorry, K thousand, no, I'm sorry, turns out to be, yes, I wrote correctly, 0.001, sorry, 1 atmosphere. 0 atmosphere. I should not write this. K has no, constant, okay, unit. K has no unit, okay, so 0.001. So, which means, which means, which means, I remove this also. I remove this. These are all over. Which means we will write this K thousand is what? For this reaction to AB square PO2 AB ABO ABO square. Okay. Now since these are at equilibrium, so what is this? What is this? This is actually has 0.001. These are one pure substance, one activity. This is one activity. Or PO2 will be how much? Well, you don't have to. Or PO2, or PO2 will be, or PO2 equilibrium, for which, because there are many PO2s, so this PO2 distinguish this PO2 from this. This is BBO. Means for this reaction, say this reaction 2, this is for reaction 1, and temperature should be specified, always 1000 K, and equilibrium is how much it is? 0.001. Now 0.001, this part is okay. As K is what is this? PO2 equilibrium. K is PO2 equilibrium. As K is PO2 equilibrium, so what is Q? In this case, Q is what? As K is PO2 equilibrium, Q will be similar expression. Q is, remember this, this is one. Q is PO2 actual. So what is the, now how shall I get the PO2 actual? We follow this. K is PO2 equilibrium. What is the value of K? 0.001. 0.001. We know this. So no problem. We'll compare Q versus K. See, this problem will give you an additional concept. So this is Q versus K. Q less than K means delta G is negative. This reaction is spontaneous. And delta G is positive means Q greater than K. Means delta G is positive and reaction is impossible. So comparison is necessary. Or you can find delta G, negative or positive, same thing. So so K PO2 equilibrium is known, 0.001. 0.001. Okay, no problem. So what is PO2 actual? PO2 actual, this is tagged equilibrium, this is tagged actual. In the first case, what was the actual? The one that I took here, 0.5. Actual, we took actual 0.5 atmosphere. But what is the actual in this case? Equilibrium is, as I have already said, K, PO2, K actually, PO2 equilibrium is 0.001 atmosphere. Q value is what? What is actual now? Now you have to understand that here this PO2 actual is nothing but what is actually present when BO is coming into the system. What is actually present? Present is 0.01 atmosphere, and that is actually an equilibrium value. That is actually an equilibrium value of the other system, AO2. So equilibrium of one system equilibrium of one system becomes the actual for the other system. This equilibrium becomes the actual for the other system, means which system it is? BBO system. So it is so BO is exposed to an actual value of 0.01 atmosphere, which in turn, of course, this equilibrium. So you may have conflicts, why it is actual but this is equilibrium. See question, confusion. Sir, equilibrium you are writing, actual writing, but it is equilibrium. It is the equilibrium for AO2, and that is actually sitting here, and this is maintained here. This is exerted here. This PO2. So it is exposed to BO, whose equilibrium value is this, which is actually namely 0.001, is exposed to a PO2 0.01 atmosphere, obtained by what? By establishing an equilibrium of AO2 and O2. But whatever may be the source, this is the actual for BO. It is going into an actual thing. This is actually present. So it is actual for this. And this actual is an equal. So Q is PO2 actual. Now, so this question I have taken. But what is PO2 actual here? This is the concept that I wanted to tell you in this problem. Okay, main. That's what is PO2 actual. Other things you already solved in assignment number 7 and practice problem. But what is PO2 actual? What is PO2 actual here? This is question. Okay, actual here. Here PO2 actual. Let me remove this. Here PO2 actual is nothing but PO2, this stuff, PO2, right? Equilibrium for the system AO2 means reaction 1. I have removed this, perhaps. I have removed this, okay, last part. For the reaction 1, this is reaction 2. For reaction 1, so that value, see, equilibrium is used as actual, and equilibrium value is used as an actual, is playing the role of an actual. This is the conflicting thing, but if you understand, no problem. See, you clearly see, yes, what it is exposed to? 0.01 atmosphere, that is the actual. What is its equilibrium value? Go to the delta G0. What is its equilibrium value? Go to the delta G0. Find K, and okay, that's equilibrium constant, and which is actual PO2 equilibrium. So, is PO2 equilibrium, what is that? This value, right? 0.01 atmosphere. So you get this. So Q is PO2. So Q is what? PO2 actual is 0.01, and K is already PO2 equilibrium is K already I have given you 0.001. So 0.001. So we see Q, hence Q is greater than K. This means delta G is positive. So delta G is positive. So it is better. Shall I write? So let me write. So this is positive, Q is delta G positive. So the dissociation of BO into is impossible. So the dissociation of BO solid into B solid dissociation of BO solid into B solid according to equation reaction 2, according to reaction to this two. What is the two? This. You will not dissociate. It is impossible. Is impossible. According to reaction to comma is impossible. So I may write here. Right. So it is better you write. Okay. Shall I write here? So we write a comment here. Comment. I remove this. I remove this. Comment. Give star. Star or double star. Double star. Right at the top. Just remove this question. It was B actually. So there will be another coming. So keep it only. But remove this question. So comment here. Double star. Comment. What we learned? What we learned here important. That equilibrium value of one system becomes the actual for another system, for the other system. So this is actually when we have two competitive equilibrium. So comment. Converse could occur. The equilibrium of this one, BOB, this system equilibrium will be treated as actual for the reaction A plus O2 goes to AO2. This is conversely true. So comment is this. This is the concept. Comment is this. So we see this comment. So actually wait a bit. Time to change the pen. Okay, wait a bit. So we see that. So we see that. So we see that the equilibrium value, the equilibrium value of one system, equilibrium value of one system is treated as the actual value for the other system. This was required. This question I raised actually to clarify this. So these are also part of concepts of equilibrium. So that's why this. See, first thing when the moment the teacher in the class says, "Oh, well, what is the actual value here? Actual for BO, actual is 0.01." But then the student will ask. Some student may ask, "But sir, this is equilibrium, sir. This is equilibrium, sir. How can it be actual?" So this has to be explained that this is the equilibrium for AaO2 system and is used, can be used as, or can be considered as the actual. Is playing the role of actual for the other system, namely BOB oxygen. This equilibrium is acting as the actual for the other system, BOB system. This is all. Okay. So this is the okay. So we have completed second point, second issue. Sorry, now fourth issue, second example. See, last example. So I will actually consider this last example. This is also interesting. So let us, in the meantime, let us remove this and clearly. So make it completely clean so that we may write on to be. I remove this also. Concept equilibrium. This is the not B anymore. This will be C. The last one. Last example about the concept of equilibrium. Let us follow. Question in the form of question answer. Question. What is the question, sir? We often see we often see the following the following APCO diagram. Figure 4 diagram, right? Figure 4. I'll soon draw it. Figure 4 in the textbooks. In the textbooks. The textbooks. Question is, can we draw the diagram ourselves? Ourselves. The first question. What is the next question? What is the minimum temperature above which carbon C carbon which carbon can reduce FeO at 1 atmosphere total pressure and reduce FeO at 1 atmosphere. FeO means FeO solid. Okay? At 1 atmosphere total pressure, but it should be very particular about specifying the pressure which was contributed by CO2, pressure of CO2 mixture of CO2 of CO plus CO2. They will constitute the total pressure, no other gas, no nitrogen or nothing else. So CO plus CO2. This is a question. So question is what? What is the minimum temperature above which carbon will reduce FeO? This is a very important metallurgical question, metallurgical query. Okay. So this is last is repeat the last question. Repeat the last question. Last question with a gas mixture. What? Now we are introducing nitrogen. This is not CO2 at a gas mixture. What? 50% or what percent? Let me check. 55%. 55% nitrogen and then CO2. The rest mixture, but still at a total pressure of 1 atmosphere. At 1 atmosphere total pressure. Total pressure. Repeat this. So 3 parts. First is, can we draw the diagram? The diagram I will draw here, and this is available in books. So can we draw the diagram ourselves? This is first question. What is the minimum temperature above which carbon can reduce FeO at 1 atmosphere total pressure? This is very important blast furnace problem and also your direct reduction problem, all these things. Okay, sponge iron. So DRI, directly reduced iron. So carbon can reduce FeO at 1 atmosphere total pressure. Of this is sometimes not written in books, but should be written. Of who are composing this 1 atmosphere, who are actually constituting this 1 atmosphere, sharing this 1 atmosphere, CO2. Repeat. Next, last part, last question, last part. Repeat the last question. This third part. Repeat the last question with a gas mixture. Now nitrogen is introduced. 55% nitrogen, CO2. This is very important, very practical, because in blast furnace we have nitrogen. Air, we blast is air, so nitrogen is there. So in presence of nitrogen, still total pressure is 1 atmosphere. What is the temperature? Will there be any change in the temperature? So let us do this. So let me draw this diagram first. Then I will say answer I am taking. I am writing here, but let me draw this nicely. Very important diagram. You have also seen in textbooks maybe. Okay, this is y-axis is percentage CO in CO2. The mixture that I have said in CO2 mixture, CO2 is y-axis. Okay, this is actually, and this is the temperature axis, temperature axis. Okay, and what is this is your 0%, 100%, and this is your obviously 50%, 50, your 50%. This is 50%, 50. Okay, 50% is in CO2. What is this? Also in other words, this is also CO by CO plus CO2. That is also, that is the mole fraction times 100 is the percentage. Actually, let me write this 50 first. Let me write 50. It is important here. 100, 0, 50. What is this? This is CO2. This is I am writing here in CO2. Right? Nicely write in CO2 in bracket. Obviously percentage CO. This is what, or it is what, right? CO by moles, moles maybe CO by CO plus CO2. Mole CO, this is mole fraction, and times 100 gives you percentage. So or, and this is moving in the increasing in this direction 0 to 100. This is 50 now, clear? This is 50. Just a scale, rough scale. Okay. Now let me draw this. Still, it's better now. This is okay. Now this is a carbon cup. A, this is 0 here. A, B, and this heats here at X. It is better I draw this side at X. At X. So this is actually, this is the one. This is what? This is the stability field for FeO. FeO. This is for Fe3O4. Solids, all solids. And this is for iron, solid. Is okay, iron, so 3 is there. So, and this is what? X, okay. This is roughly, or why roughly? This I know. Temperature, remember it is degree centigrade I am writing, temperature, degree centigrade. So, because centigrade is popular, 575, this temperature. Everyone knows this temperature, triple point they call it. And this temperature, also everyone knows, this is about 700 degree centigrade. Well, this much is okay. And what else? What is the, this is point C, say, Cx, let us consider another point, Z or Y actually, Y. Consider another point, call it Y, D, Cx, Y, D. Okay. Y is, say for example, if you ask me what is the Y temperature, 800 XY. Okay. Very good. Very good. Okay. So this is the figure 4, APCO diagram. Actually, let me explain this. What is this equilibrium? Let me write. This is actually, this is the carbon. You write here carbon saturated line. Carbon saturated curve. What is this carbon saturated curve? Okay. Also, carbon saturated curve AXB. This is 0 here. Carbon saturated curve. What is the name of this? AXB. Follow. AXB. Okay. It's about 0. This is okay. What is this? Here carbon saturated means what is the equilibrium under for which you have drawn this? CO2 plus C is 2CO, and carbon saturated means activity of carbon is 1, and also you should write here P total is 1 atmosphere. At 1 atmosphere total pressure, as I have mentioned, the total pressure of CO2, this is wrong. This is the character of this curve. What is the curve? AXB. B here. Okay. It's okay. Clear. And what is CXYD? This curve is curve C X, capital X, Y, D is equilibrium APO plus CO goes to AP plus CO2. This. So this reaction, two reactions, okay? CXYD. Okay. This is the current state of affairs, okay? What is the percentage CO this side in CO2 mixture? This is okay, it is okay. So what 3 temperatures I have? 575 is the point C. Okay, this is called triple point. I don't want to discuss this. 700 is the temperature where this carbon saturated curve, or carbon line, I say simply carbon saturated curve. This carbon line intersects the APAPO line. This is APAPO. If you ask me what is this, this is also APO-APA3 equilibrium. And what is this? AP-AP3 equilibrium. I am not discussing this. I am interested about carbon and APO. So this is the carbon curve. This is AP-APO curve. They intersects at X. At a total pressure of 1 atmosphere, this is drawn. Because why it is important? Because if we change this pressure, you will see it will shift. When the total pressure is, this will shift. I will soon take up this. Very good. Achha. Let me first of all answer the first question. Can we draw the diagram ourselves? Let us see. This, yes, we can very well draw. We can very well draw the diagram ourselves. Ourselves. We will draw the diagram ourselves. Okay. And in fact, and in fact, and in fact, we should we should endeavor we should endeavor spelling is okay, endeavor, we should endeavor to draw such diagrams, to draw such diagrams, such diagrams, particularly the simpler ones, particularly the relatively simple ones. Simple ones, ourselves, ourselves, in order to, in order to have good comment, have a good comment over the diagram. For example, if a software draws the diagram for you, then you don't understand actually. You do one thing, you can take help of software, but before that you try to draw the diagram yourself. Then compare this to yours and the softwares. This is possible, or once you are, then you will be able to actually decipher the curves, or you will be able to understand the different equilibrium curves, and they are actually and can assess the relative stabilities of different compounds and metals. So you have control about the partial pressures, temperature, what. If someone draws for you, then you will actually copy this and just you say, sir, this is the stability field, etc. It's a very easy, very facile remark. Okay, very rudimentary things that you will be able to tell about the diagram. But it is your credit. It goes to your credit if you can draw the diagram yourself, particularly the simpler ones. Okay. Then if it is very complex, then you can take a help, because by that time you have already understood how to draw the diagram. You know, so you can actually interpret the diagram well once you know how to draw the diagram. Okay, and you can draw some diagrams. So next is we will learn we will learn drawing such diagrams, such stability drawing, different types of stability diagrams, different types of, these are called stability diagram, different types of stability diagrams, stability diagram, including the one in figure 4, in figure 4 later on. So we will also draw this diagram ourselves, but later on. Okay, when I will discuss Gibbs phase rule and construction of stability diagram, they will take up this. But this is given. Okay, So as I repeat, this is a carbon saturation curve or say carbon line, short carbon curve, carbon line, and this is the APAPO equilibrium line. These two, consider this curve and this curve, CXYD and AXB, this carbon curve. This is actually tussle between these. This is actually then, and these two curves will decide what is the minimum temperature above which carbon can reduce. The answer is answer. Okay. This first part is okay. Can you draw the diagram? What is the minimum temperature? Okay, next question. The minimum temperature, the answer is X. Answer is X. Where it intersects the PPO curve. This is the minimum temperature above which carbon can reduce. This is the answer. Answer is easy here. So let us write this, okay, on records, keep it on records. The minimum temperature above which carbon can reduce APOs, carbon can reduce APO, means APO solid, and carbon is also solid, can reduce APO at 1 atmosphere. APO solid, you may add also. APO solid at 1 atmosphere, total pressure of CO2, of CO2, of CO2 at the total pressure CO2 is given by is given by point, which point? Point X. Point X, which is 700 degrees. What is this temperature? 700 degree. 700 degrees centigrade approx. Okay. So this is the answer I am giving. Okay. The reason is this, approx. The curve, I am writing again, the curve AXB. AXB. Sorry, sir. Sorry. The curve AXB represents the equilibrium What equilibrium? CO2 gas plus carbon solid. I've written here. Is 2CO gas. 2CO gas. Okay. Under carbon saturation. Very important. Activity of carbon is 1. Carbon saturated curve. Under carbon saturation. What is the meaning of saturation? In terms of activity, activity of carbon is 1. Under carbon saturation, at 1 atmosphere, again at 1 atmosphere, total pressure of CO plus CO2. At point X, so this, what I have written here is written here, in short. Okay. At point X, this curve intersects the FEPO curve, FeO curve, which is given by what? Tell me. Curve, which is given by C FeO, this curve, FeO curve, Fe up, FeO below. This is what curve? This is what curve? FeO Fe4 curve. This is what curve? What curve? Fe3O4. And what is the reaction here? FeO plus CO goes to Fe plus CO2. Similarly, here it will be Fe3O4 plus CO goes to FeO plus CO2. And likewise here. So, additionally, I am talking about this. Our interest only in these two curves. See, let us see. There is a the curve intersects the FeO curve. Which is the name of this curve? CXYD. C, remember C. Already written there. C, sorry. C, yes, okay. C, X, Y, D. C, X, Y, D, FeO curve, FeO curve. At any temperature, and this is the minimum temperature, and any temperature greater than X, at any temperature greater than X, at a temperature greater than X, say temperature Y, say temperature Y, which is Y, at any temperature greater than X, say Y, which is 800 degrees centigrade. 800 degrees centigrade, the carbon line lies above. The carbon line means, carbon saturated curve, lies above. See, carbon at this temperature, this is the FeO line, this is the carbon line. So at this temperature, carbon line lies above the FeO line. Okay. So if it is better, I actually give you this. If this is Y dash, Y dash, Y dash, and this is Y. Carbon line at Y dash, FeO line at Y at the temperature 800 degrees centigrade. That is the temperature. Okay, at this temperature. One is Y, so this is above. If it is above, then it can reduce. But let us explain this. Carbon line lies above lies above the carbon line lies above the FeO line. That is actually, I remove this part. This part. This part is good enough. That is, give a star. That is, that is CO by, that is, write this, CO by CO2, carbon saturated, 800 degrees centigrade. Shown by point, which point? Tell me. Carbon line is what? Which point? 800 degrees centigrade. This point is Y prime. Shown by. Is what? This is what? This is greater than CO by CO2 of this. These are the CO by CO2 comes from the Y axis. this is greater value of y, and this is less value of y. Y axis value, percentage CO. Less percentage of CO here, greater percentage of CO. What is that? CO by CO plus CO2 or CO by CO2. Many ways you can write percentage CO. In the CO2 mixture, I have written correctly. It is y prime, and this is purely y to y prime. It is y prime. So one is above, another is below. So so CO2 again CO2, which this is APO. Equilibrium is, as you know, APO, again same temperature, 800 degrees centigrade. 800 degrees centigrade, and given by shown by point y, shown by point y. This is y prime. So y prime above, y below, shown by point y. Okay, as can be read off from here. See, which is CO by CO2. This is percentage CO, means CO by this. You will get CO by CO2 also. Same. You check this. CO by CO2 increasing. So CO by CO2 is greater for the carbon curve. CO by CO2 is less for APO curve. So this I have written. From this. If you go from the read of the y-axis. So this is here. This is here. So good boy. So, so as can be read of the y-axis. y-axis, which is nothing but that is percentage CO axis. I have said percentage CO axis. Okay. Is greater. Hence, since it is greater, hence carbon is capable of C is capable of reducing APO to AP in compliance with the spontaneity of the reaction. What is the reaction? APO will be reduced to APO solid plus CO gas goes to AP solid plus CO2 gas. In compliance with this equilibrium, with the spontaneity of this reaction. This is okay. This is the answer. Okay. Okay. This is, now you may ask me at this stage. You may ask me, sir, why if it is above, why it will reduce? Carbon line is above. See, you have seen at any temperature above X. Sorry, I cannot touch it actually. At any temperature above X, you see always carbon line above. There they intersect. Greater than this, carbon line above the APO line. Above more. See, this is the difference. So any temperature greater than this, carbon will reduce APO. So what is the minimum temperature? If it is asked, you will say critical temperature is what? Sir, 700 degrees centigrade. And carry out experiments above 700 degrees centigrade at a total pressure of 1 atmosphere. Remember, if the pressure is different, then I will show you soon actually. That is second last part. But before this, you may wonder why this reaction is Spontaneous means delta G negative. So which reactions are delta G negative? And if it is Q or Q less than K, so that Q less than K or delta G negative, then we will appreciate. Now see explanation. You follow this. Just wait a bit. Explanation I am giving, you will follow. Then again you will see I am using the previous concept. Explanation. Quick explanation. Suppose you are studying the reduction of FeO by CO2, by CO gas. Suppose we are considering the reduction of FeO into Fe according to the as follows. What is this? FeO solid plus CO gas, Fe solid plus CO2 gas. I am removing all this. I think you don't. Now tell me, in the language of Q less than K. So we know for spontaneity, follow this. For spontaneity, Q should be less than K, or another way you can write this. What? 1 by Q greater than 1 by K. Same thing. Okay. This makes delta G negative for spontaneity. Okay. So we'll try this. For this reaction, so what is the K for this reaction under study? So we will consider this is our reaction and it is exposed to something else. So K is what? What is the K? So right here. This is required for spontaneity. Now find K. Which one I am writing? FeFeO. You don't mind FeFeO. And temperature say 800. That temperature 800 degrees centigrade. Remember, not Kelvin. It's centigrade. Is what? What is the K? Tell me. K is what? See the reaction. Again, you know very well activity of Fe, PCO2. PCO2 by activity FeO. PCO. And you know these are one. Pure solid is PCO2 by PCO equilibrium. Here also given equilibrium is also equilibrium. So it is your K. K equilibrium. What is the K actual? Q would be what? Sorry. Q is what? PCO2 by PCO actual. You are studying this. Actual is something else which is exerting a CO2 on it and applied. Actual is applied by something. Its equilibrium is this. What is equilibrium is this? Actual. Acha. What is this? What is PCO actual? Who is giving this? By the way, acha. What is this? Here, right here for additional FeO. Okay. What is the PCO2 actual? Is PCO2 actual, right? Temperature also give 800 degrees centigrade since we are discussing. This is also coming from which one? This is exposed to FeO is exposed to carbon system. So PCO2 by PCO, carbon will also give CO2 through the reaction CO2 plus H2CO. So it is actually actual is what? For this equilibrium, this is actual. For the equilibrium of FeO, carbon is the actual. Carbon reaction is the actual. CO2 plus H2CO is the actual one. And the PCO by PCO2 that which is obtained from this will be actual. So is what? PCO2 by PCO, write this, actual coming from what? The equilibrium for, this is another equilibrium, this is the actual, but this actual is an equilibrium for the other one. Because this is the equilibrium diagram. This whole thing is a stability diagram, is equilibrium diagram. So PCO2 by CO equilibrium for which? For CO2 plus C is 2CO, you may write this, or carbon saturated curve. This curve, what is the CO2 CO for this curve? This curve, this is the percentage. So this is, you see, you read this CO2 by CO. Achha, this is the Q. Now 1 by Q by 1 by K will be better because it is, these are CO2 by CO. By 1, I want CO by CO2 because then it will be directly to the percentage CO. It is, see, PCO by PCO2, you may write. See, PCO by PCO2, percentage CO. So you write 1 by K, then 1 by K is what? You write here PCO by PCO2. Write once more from this. 1 by K is PCO by PCO. Right here, you don't have to write here. Is equilibrium. Write equilibrium very much, because equilibrium and actual is in see here, actual and equilibrium. Contrast. See the contrast. This is actual. This is the equilibrium value for carbon, but is treated as the actual for the reaction under study. Is actually imposing a CO2 on the reaction under study. Is behaving as the actual. Is treated as the actual. Is being used as the actual. Is playing the role of the actual, but obtained from the equilibrium of the other one. Second one's equilibrium is the first one's actual. So 1 by K equilibrium what? You write this FeO. This is very easy, from delta G0. How you get this? Delta G0. From delta G0 you get this. Okay, that is very easy. Equilibrium constant. Always delta, here also delta G0. So K, okay, happy? 1 by K. And 1 by Q is what? Tell me. PCO by, right, nicely. 1 by is okay. It is 1 by Q. Q is what? Right? PCO by PCO2. Right? Actual. But you have to write, but it is equilibrium form. Equilibrium CO2, right here. CO2 plus C is 2CO. Am I right? CO2 to CO. You write this way also. CO2 CCO. Carbon curve. Temperature in either case 800. Since I am discussing 800. Why 800? Any temperature greater than 700. Minimum is 700. So 800. I should not go below this. Now what you see? 1 by Q greater than 1 by K satisfied? What is the 1 by K? 1 by Q first of all. What is this? This PCO by PCO2 carbon curve. This point is Y prime. Okay. So I'm writing here. This is Y prime. See, this is Y prime I'm writing, and this is Y. Achha, showed by point 1. Showed by point Y. Showed by point Y. Yes, is a PCO by PCO2. This is a PCO by PCO2. This percentage CO means PCO by PCO2, or say some form. Okay, you can find this. From this you can get PCO by PCO2. So this will also follow in the same manner. See, PCO, if PCO increases, percentage C increases. So no problem. PCO by PCO2, since carbon means carbon line is this. So this Y prime, this point. So this point is Y prime. And this is shown by, right? Shown by. This also right. Shown by point. Which point? Tell me. Point. Which point? Y prime. Point Y prime. Carbon Y prime Y. Which is greater? Sir, 1 by Q carbon, 1 by Q CO2. This is 1 by Q greater than 1 by K FeFeO. CO by CO2, 1 by Q greater than 1 by K means Q less than K, means spontaneous. So carbon will reduce. This can be shown easily. So you see, once again you get the good answer that what is the minimum temperature above which carbon can reduce FeO. These are this metallurgical question, very important question. You get this answer, but remember it is stacked with the total pressure of our atmosphere of CO2. Okay, so this you have answered. First of all, minimum above 700 degrees centigrade. Since they have actually intersected here, this is a critical temperature. Above, not below. Below actually this will be below, this will be above. I want carbon cup to be above, so that CO by CO2 carbon should be greater than CO by CO2 of FeFeO, and reduction will occur in this for this reaction. Okay, this is okay, and so this okay. I don't want to discuss. I will take up on the last. Repeat the last question with the gas mixture. I am removing this. Don't mind. The last part, the very last part. With this we have complete the concept of equilibrium. Fourth issue. Last part is with a mixture of. So now we just when the last part, right? This last part better. Last part. When the CO2 mixture is diluted with nitrogen, what happens? Is diluted with nitrogen 55%. 55%. Here 55% nitrogen at a total pressure of 1 atmosphere. Total pressure 1 atmosphere. The effective total pressure of CO2, that is PCO plus PCO2, is what? Tell me. 1 minus 0.55 is 0.45 atmosphere. So it should be CO2 only. So CO2 total pressure is 0.45 atmosphere. This line is drawn for 1 atmosphere, and it can be shown that if the pressure changes, this is a pressure sensitive equilibrium. At low pressure the reaction moves to the higher percentage of CO, and higher pressure moves to the left, means higher percentage of CO2. So pressure dependent. So that's why this is for 1 atmosphere, you have to specify. And now since this is diluted with 55% nitrogen, now the effective pressure of CO2 is 0.5. So I have to draw another line for 0.5 atmosphere. Okay, so 0.5 atmosphere. So we see that what we see, let me do this. I will use just a different color if it is. Let us see. I am drawing this. I am drawing this curve. This is good enough. Okay. What is the name of this curve? It is A. This is A dash. And what is this? This is called. These are Y are used Z. Z, and it is B dash. B dash. A Z B dash. So this is actually the one. This is for what you write here. I write this. I write this. It is not good. This pen is not showing well. So this is what is right. Right for P total is otherwise same. Okay, you write here. Right here. Better you write here. This side. This is there is some. This is carbon saturated, like this carbon saturated car. Carbon saturated car. What is the difference between these? The P to P total. Carbon saturated means activity of carbon is 1, and this equilibrium is again same. I am not writing. They are writing the P total. P total is 1 atmosphere. P total is 1 atmosphere. I wrote here. I should have written here. P total is PCO plus PCO2. As mentioned there, there is a total pressure of CO2 1 atmosphere. So, and then write 1 atmosphere. Then write 1 atmosphere. Now here similarly write P total is again P total PCO plus PCO2 was what? What? 0.45 atmosphere. You can very easily see that it will move to the left. Move to the left. Why? Why? See, so given temperature, you see, as pressure is decreased, given pressure is decreased, at a given temperature, say here, pressure is decreased, percentage CO is increased. Let us see, follow this equilibrium. As pressure is increased, as pressure is pressure is decreased, percentage CO increase. Pressure decrease means the reaction moves to the greater number of moles, to the side where having greater number of moles of gas, 2 CO against 1 CO2. So lower pressure will help the reaction move in the forward direction, to the direction of CO. So greater percentage of CO at lower pressure, and this also happens at lower pressure. This green line, this green line lower pressure, this upper pressure. Given temperature 700 degrees, for example, 700 degrees centigrade. So this is this, and this is this. So percentage CO has increased this. So it should move to the left. Okay, should not move to the right. So it is drawn correctly, and you will draw this diagram. Okay, very important diagram. You will draw yourself when we will discuss stability diagram. So we see that now. What we see, the Z. What is the temperature of Z? Shall I show this? Z is what temperature? I am not sure because I have not calculated this. No, so I am writing this is 6. So right here, it is better I write here. Right here, right here. 650. Oh, simply not. I have not calculated for this one. So say I have said say. but it is any temperature less than 700 degrees centigrade. This one. So Z. We see that. Let us write this out. We see that the carbon saturation curve this time intersects the FE curve at where 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 at Z. This curve intersect this curve C X Y D curve. FEPO curve intersects at Z instead of at X, previously X. So at Z at Z I am not very sure. So I have written here 650 degrees centigrade, say maybe close to this, but it is to the left of this X, to the left, means lower temperature than 700. That I comment here. So remove all these things. So it is better write in case you have. Okay. So the minimum temperature. What happens to the minimum temperature previously? What was for 1 atmosphere CO2? What is the minimum temperature? X, 700 degrees centigrade. Means any temperature above this will enable carbon to reduce APO. And now the minimum temperature is what? Critical temperature is Z, which is 650 degrees centigrade, say. So now what has happened? So any temperature above 650. So critical temperature has been reduced. This is the change. This is the effect of the dilution of CO2 by nitrogen. And this also simulates the blast furnace where nitrogen is present actually. So we can write so the minimum temperature. So the comment, so the minimum temperature above which carbon can reduce APO solid under this condition is 650 degrees centigrade as different from 700 degree previously X 700, now Z 650 is 650 degrees centigrade, which is less than 700 degrees centigrade. Which is less than 700 degrees centigrade obtained in the first case. Obtained in the first case. First case means this case. This one. This one. First case, second case. First case, second case. First case, total pressure of CO2 1 atmosphere. This is the total pressure of CO2 is how much? 0.45 atmosphere. So we see we can actually have a limiting value even less than 700 degrees centigrade. So now we can say at any temperature above 650, like say 655, 660, 670, etc., you can carbon can reduce APO when the total pressure is what? Total pressure is of CO2 CO plus CO2 0.45 atmosphere. This is the message. So so with this actually, so we have completed. So let me comment here. Okay, answer is over. So I am removing this. So with this, let us finish this last line. With this, okay, can here give a double, triple star perhaps, triple star, start here, triple star. With this, we have finished the topic. Finish the topic. 4 issues that make thermodynamics a difficult subject, a difficult subject, for the students. For the students. For the students. We have completed. Next class, what we'll study? Gibbs. Next class, Gibbs, Duhem equation. Hello, Bapu. কি করছিস রে? এই next class, Gibbs-Duhem equation, which will be followed by the integration of Gibbs-Duhem equation. So first we will take up Gibbs-Duhem equation next class. So with this, we have completed today's lesson. Thank you very much for your cooperation and for your interest and for your devotion, etc. So thank you very much. So today we will actually say goodbye and we will meet next class. Thank you.